All right. So I think a couple orders of business as we get started. So number one, I think I need to put in a work order to get some extra tables in the back. The other thing I think I need to do is, well, maybe I don't. I'm not sure. So just a heads up. I did a quick straw poll. Looks like most of you have been able to get the software installed. I'm going to ask you again next week. For those of you that haven't, it does seem to be that the most common issue regarding the software installation is the software not showing up when you log into your account. Just a heads up, there's some chairs out there in the main lobby. They're the small green ones that you can. Yeah, there you go. It seems like the most common error is that the account or that the software is not being listed when you log into the account. If you encountered that error, I put in a work ticket in with IT to see if they can refresh their institutional list, but you might want to try and log in again because we had one student who was encountering that error, and then this morning he logged in and then it was there. So IT might have refreshed something and whatnot. But keep in mind, we will have our help session on Friday in 11:01, or sorry, in room 3235 from 11 to 1. I will mention that we are going to have a guest TA in that help session, and I'm going to have to bounce for a little bit because my daughter has a half day of school, so I have to go pick her up. So she's probably going to be hanging out with us for about half an hour. So, but just don't upset her, or she'll give you an F. So that's a joke, not a funny one. So did everybody get the code? Okay, all right. So just a couple housekeeping items. I do have the attendance grades from the previous lecture posted to Blackboard. I do have the lecture recording from the last lecture posted to the YouTube playlist, and my goal is to do that I'm trying to keep up with that so that it's not not too much of a lag there. So let's talk about assignment 1, which is going to open up today at 1 p.m. It is going to close Wednesday at 10 a.m. So the idea is that by the time we come back to class next time, the assignment will be done. Just a heads up in terms of how that assignment is structured. We've got some folks grabbing some chairs in the lobby. If you want to grab one, you can sit down. So, all right, okay. The way this assignment is structured, I'm just trying to get some data on the gradebook for everybody. So this assignment allows unlimited submissions, and it will take the highest grade, so it really shouldn't be very difficult. It's going to largely be focused on what we talk about today. So I do want to get into that. Does anybody have any questions before we get started? Okay, all right. So I must, I guess, briefly apologize for the fact that today's lecture will seem kind of dry, but it is very important because this entire course is intended to educate you on the process and procedure for generating engineering drawings. And I think that the first thing that we ought to do is look at some and look at the common components of engineering drawings and how things are supposed to be properly formatted and things like that. So I have a couple of drawings here that I kind of want to take a look at. And so I'm going to begin with this. I'm calling this a mechanical engineering drawing, and I want to give a quick disclaimer now at the start of the semester. So we've got civil engineers, mechanical engineers, biomedical engineers, I think some industrial engineers here as well. I would say for you mechanical and biomedical engineers, and probably even the industrials as well, a lot of what I'm saying here, when I say mechanical engineering drawing, I'm probably referring to all three of you. So as an example, a mechanical engineer would very obviously generate a drawing of something like this. If we were looking at a biomedical context, if you were generating a drawing of let's say a bioimplant device, the device would be different, the scale would be different, but the engineering schematics would probably be very similar. Civil engineering drawings are going to be a little bit different in that while civil engineering drawings also are sort of part and schematic based, a lot of their drawings are sort of mapping based. They're drawing maps of land areas and things like that. And so there is a little bit of difference in what you see there. But this is a very representative mechanical engineering drawing. This is a like a flange housing part and whatnot. And let's sort of like take stock of what all we see here. So the first thing that I think is noteworthy is that this is all a drawing of one part, okay? Particularly, this is all representations of this part. And what we see is the same part represented multiple different ways. We see a lot of two-dimensional views of this three-dimensional part. So this is like looking at the top of the part. This is looking at the bottom of the part. We also see what are called section views. So this would be if you take the secret weapon of engineering, which is a samurai sword or a lightsaber if you happen to be a sci-fi fan, and you cut through the piece, what would it look like if you cut through it? And so you can sort of see the insides and the varying diameters of the piece and what have you. There's also a series of annotations. We have dimensions, basic information about the company that produced it and what have you. And there are some common elements which we do see here. This is an example here of a civil engineering drawing. And so there are a lot of common elements that you would find in those contexts. There are some differences though. For example, in a civil engineering drawing, you will probably be less likely to see full-blown dimensions because instead what you're seeing is a plan view of a given construction area, and what is more important is that it is drawn to scale. And so the idea is that if you need to determine some distances, you can infer them, ensuring that the drawing is printed to an appropriate scale. But there are also, some very similar things. We have, again, the title block representing the company that produced it, a series of annotations, things like that. Because this is a mapping project, it might seem silly, there's a north arrow. You wouldn't see that on a mechanical engineering drawing. Some other aspects that sort of make the drawing complete. And that idea of completeness and a lack of ambiguity is one of the chief goals of a series of engineering schematics. And so we need to if we want the drawings to be complete, we need to know what needs to be on them. Okay, so that's kind of the idea of today's lecture. Okay, so what goes into an engineering drawing? Okay, if we look at both of these drawings, let's maybe start talking about what makes these drawings alike versus what makes them different. Okay, so I look at both of these drawings, and one of the first things I see is that both drawings have a page border. Okay, so in other words, we have the sheet of paper, and then there is a border, and all of the drawing, the schematics, the text, all that is housed within that border. Okay, nothing goes outside it. Okay, and that's true in all contexts. Here you can see, like, here's the page border that's just inside of the actual physical border of the page. It's commonly, usually around 1/4 of an inch or 1/2 inch away from the edge of the paper, and that's actually 1/4 of an inch is actually what we'll use for this class. You will also see on both drawings what's called a title block, and so on the mechanical engineering drawing, that's this part right here, and on the civil engineering drawing, that's this part right here. Obviously, the drawings both contain the parts or components of what they're intended to represent, so or the mapping project or the flange housing part and whatnot. What about the objects themselves? We have lines, we have arcs, we have circles, we have ellipses, we have hatches, we have all of the different objects that construct the features that we're intending to draw. Dimensions, we have a series of notes that identify how big certain or small certain pieces are and whatnot. Finally, we have our annotations and our scale. So let's talk about each of these in some detail. Okay, so the first thing that's probably worth mentioning is the paper that these are printed on. Engineering drawings they typically are printed on standard sheets of paper. So the reason I mention this is because if you open up AutoCAD or Inventor and you start producing drawings, like you generate some file and then you try and plot it to a PDF or try and plot it to a printer, you have to specify both the size of the drawing and the scale of that drawing. See, it's not like Microsoft Word. Like Microsoft Word, you can just type something out, hit print. There you go, right? In AutoCAD, because we're producing drawings to a specific scale of a specific component, we need to specify the paper size. We need to specify the scale to which it's drawn. ANSI are the standard sheets in the United States, and that's the reference that that AutoCAD and Inventor use. So, for example, you all are probably well familiar with letter paper, 8.5 by 11 inches. Okay, in ANSI standard, that's an ANSI standard size A sheet of paper. So that's 8.5 by 11 is ANSI A, and 11 by 17 is an ANSI B. Okay, and ANSI C is a 17 by 22, and so on and so forth. To give you kind of an idea of a schematic of what that looks like, this is sort of like the idea of what they look like. So for example, if I look right here on this image here, I don't know if you can see my laser pointer here, but this is an ANSI A, this is a letter paper, 8.5 by 11. And so if I took two letter papers, like an 8.5 by 11 and an 8.5 by 11, and I taped them together, I would get an 11 by 17, I'd get a B, right? So the idea is like two A's make a B, and then two B's make a C, two C's make a D, and so on and so forth. Does that make sense? So that's kind of the idea on the size. And that's kind of important because, I mean, if you're an engineering firm and you're stocking, paper, that's how they get stocked. I do mention architectural paper sizes, not because we're going to use them in here, but because when you are plotting in AutoCAD or Inventor, at least in AutoCAD, architectural paper sizes are also an option, but we're not going to use them. And the difference is that architectural paper sizes are just a little bit larger. So for example, an ANSI A is 8.5 by 11 and architectural is 9 by 12. So it's just a little bit bigger, but we're not going to use them. So, okay. So let's talk about the title block. And so every engineering drawing is going to contain some degree of a title block. And the title block typically contains two sort of sets of information. And the way I describe that is it contains general information and specific information. So the general information that it would contain would be like the data about the company, the data about the project, right? So if I'm producing drawings, let's say I'm producing drawings to manufacture this table right here. Let's say it takes 15 sheets of drawings to produce the drawings for this table. Well, every sheet in that drawing set is going to have the drawings from, I don't know, Michelson Engineering Incorporated, the same date, the same job number, the same project number. But then each sheet is also going to have some different information because sheet A might be everything together. Sheet B might be the drawings for the legs. Sheet C might be the drawing for this, exploded views and so on and so forth. So that's sort of what the title block contains. Getting into the weeds a little bit, it will typically contain the drawing number. So in a drawing set, each drawing is going to have a specific number, a title and a description for that drawing, the company info, and by that the name, the address, the scale of the drawing, and I'm going to get more on that here in a little bit later. Any notes that are relevant, any specifications that were followed, any like ISO standards, AISC standards, what have you, to generate that part. And then info on the designer and the drafter. It will typically contain info such as who designed this part, who drew the part, who checked the design, and so on and so forth. Here's some, I guess, some more zoomed in title blocks just to give you kind of an idea. So this is sort of what I meant when I said drawn, checked, and approved. So you might have a slot here that says, some person drew it, some person designed it, some person approved it. You also might have what's called a revision table. So the idea is that will tell you that as designs get revised and iterated, you'll know that you're operating according to the latest set. So that's also pretty common and what have you. Sometimes the title blocks are on the bottom, sometimes they're on the side. It just depends on the format of the project and what have you. But that's kind of what goes into into a title block. I'm just curious, does anybody notice something? I want to look at this title block down here. Does anybody notice something about the text?
Very clear.
Very, very clear, but I'm a little more fundamental. What? It's all caps, right? Does everybody see that? It's in all caps. It is traditional on engineering drawings that the text is all caps, okay? We typically write all the text on engineering drawings in fully uppercase. So just throwing that out there for the work that we do in this class. It is pretty rare that you will see lowercase. And if you do, like if we look over here on the left, usually the lowercase stuff only refers like to the company, like the company name and address. When we get to the specific engineering aspects of the schematic, it's usually all uppercase. Okay, scale. Let's talk about scale. So oftentimes engineering drawings, the engineering drawings, they often need to illustrate parts that are either far bigger than would fit on a sheet of paper or far smaller that you wouldn't be able to understand what was going on without some degree of magnification. So to make the point, I design bridges. If I were to print the drawings of a bridge on a 1-to-1 scale, I would need a really big sheet of paper, right? So the idea is that I would take that bridge drawing and I would shrink it, right, to some known scale such that it would fit on an 11 by 17 sheet of paper. And for you, let's say mechanicals or biomedicals who are rolling your eyes at the bridge example, what about an example of some sort of, bioimplant device or something that's going in the human body that has a screw about that big? You're going to have to blow that up so that you can read the drawings and read the dimensions and read the schematics. So whether you're reducing the size of a schematic in order to fit it on a sheet of paper or blowing it up so that you can read what's going on, you do need an understanding of scale. So a 1-to-1 scale would be, would sort of be what we've got going on right here, where literally if it's 3 inches on the sheet of paper, it is 3 inches in the real world. And so that's sort of the basis, and anything above or below can be reflected accordingly. We'll talk more about scale later on this semester. Okay, dimensioning, okay? No engineering drawing, no schematic, and it doesn't matter what context we're talking about, would be complete without information regarding dimensions in some fashion or another, okay? So I have here a part above that shows a series of dimensions, and those dimensions are necessary in order to fully fabricate the component. The idea is that drawings need to be unambiguous and they need to be complete, okay? One thing I'll mention, then I want to go through a quick example to make sure we're all on the same page. When it comes to dimensions, and again, I use this term mechanical engineering drawings and civil engineering drawings. This is one of those instances where if I'm saying mechanical, I sort of mean biomedical and industrial and all that. But mechanical engineering drawings tend to express dimension explicitly, and by explicitly, I mean what you see here, like actually saying, this is 30 millimeters, this is 76 millimeters. Whereas civil engineering drawings tend to express them implicitly. In other words, here's the drawing, here's the map, and we will print it to a known scale. Anything that's important that is spelled out, anything that you need to infer, that's what you have a scale for. There are some exceptions to this. So if I was drafting out the structural drawings for the floor plan of a building, I would probably express the dimensions explicitly there. Does that make sense? Now, one thing you want to go through is how many dimensions are enough. I'll get to that here in a bit, but one thing I'll say about dimensions, and I'll talk about this more explicitly, is that you typically want to express as few dimensions as needed, not as many. We'll get to that here in a bit though. Okay. Let's talk about the annotations. And so when I say annotations, I'm basically talking about text that's included on an engineering drawing. And so some examples of what I mean by the text that's needed on a drawing are any notes that contain supplemental information, like how something's supposed to be fabricated, any tolerances that are necessary, what codes are being followed, what specifications are being adhered to. Any references, like if you're referencing certain documents or other drawings or anything that the fabricator or the contractor or the manufacturer needs to know. Again, the standard convention is that text is in all caps, okay? I have here an image from AutoCAD. These are two really, really common fonts that we use in engineering drawings. You had mentioned that they are very clear. We have a very specific font class that we tend to use in a lot of our engineering drawings. Roman S is a very common font. It sort of looks like, I mean, when I first started seeing this, it sort of reminded me of, like when I was in kindergarten and I was doing writing practice, like this is what the letters would look like, but it actually does look pretty clear on engineering drawings, which is why it's used. Architectural drawings or blueprint type drawings are a little, have sometimes used blueprint fonts, which are kind of fancier. This is a city blueprint font that I've seen a lot on like residential and commercial construction project type drawings. So I throw that in there. So we might use both. We'll definitely use Roman S quite a bit, but city blueprint we might use here and there. Some additional items that you might find on engineering drawings. So like I said, you might find a north arrow. You also might find a scale block. One of the ththings about I'll mention about the north arrow, I don't want to go past this. North arrows don't always have to be facing upwards on an engineering drawing. Typically, what you want is for the engineering drawing to be easy to understand. So like, for example, if I was generating a set of drawings for the floor plan of this building, what would probably make sense is, this building is kind of rectangular. So I would kind of have like the floor plan sort of align with the direction of the paper, but north might not be perfectly up. North might be a little bit like that. That doesn't matter as much as just making the drawing easy to understand. So north might not face perfectly upwards on a drawing. Scale blocks are sometimes used. Sometimes you'll have a scale block. Sometimes the info will just be on the title block. And you can have different scales horizontally and vertically. That's a pretty civil engineering aspect though as well. Sometimes you'll see a bill of materials. So a bill of materials, let's go back to the table. So the table might be, okay, we need 1 tabletop, 4 legs, 12 screws, 4 bracket plates, what have you. Like the bill of materials is just the list of parts that go into the project. And so that's good for quantity takeoffs and whatnot. You might also find an engineer's seal and signature. So that's actually my engineering seal right here, but you might find a seal and a signature for anything that goes or that needs a PE stamp of approval. Okay. Any questions so far? Okay. Let's talk about views. An engineering drawing and by its nature, just the idea of taking apart and representing it in a two-dimensional medium is just that. So, like, just to sort of make the point, I have here a house, okay? And I would propose that from an orthogonal perspective, and orthogonal is just a fancy math word for right angles, right? So I would propose that there are 6 ways of looking at this house. So we could look at the front view of the house, we can look at the rear view of the house, we can look at the left view, the right view, the top view, and the bottom view, right? Now, for the purposes of this house, so what we're doing is we're basically saying, okay, if I was standing here and I was looking at the front view of the house, what would it look like? And I would draw this front view, and this is what it would look like. And I call that a projection, okay? And so in the case of this house, each view offers unique information, okay? I would argue for that if I was producing drawings for this house, I would probably use all 6 views or some variation of all 6 views because every view gives me new information, okay? Every view gives me something new that I didn't have before. And so we have 6 standard views that we can define, like the front, the top, the bottom, left, right, and rear. One of the things that I'll mention here a little later is if you're the engineer producing the drawings, like what is the front? Which side is the front? And I'll give you some guidance on how to do that. It's going to be your job to tell the fabricator how to generate this schematic. You got to, make sure that's clear. So what we're doing with this orthogonal projection method. And I'll say this is probably getting a little bit into the weeds on for, I guess, a first day understanding of this. But when we generate an orthographic projection, the idea is that we're not, it's sort of like, do you remember, maybe it was probably like a high school art class where you would draw like 3D objects in perspective, and you would sort of like draw everything to where it was all sort of going towards a given point. We're not really doing that in engineering drawings. What we're doing is drawing, assuming all the light sort of goes orthogonally or 90 degrees. So, you know, imagine, you know, if it's actually 6 inches, it's 6 inches on the schematic. You're not, you know, doing this ray tracing thing. Say, oh, it's actually 8 inches if you're this far away. We're not doing that. We're just keeping the dimensions or the schematic simple and straightforward. The most common projections that we will use is front, top, and right, or front, top, and side. So if you ever think, if you ever have an object and you need to represent it in sort of a standard orthographic projection, you would typically use 3, front, top, and side, and I'll show you some examples of that here in a bit. The one thing I would mention is that as you're drawing an object, you might find a situation where some lines are hidden. Okay, so just to sort of make the point of what I mean by that, I'm going to test my 3D art skills. So let's say I just have like a box, right? Okay, and I have a box and I have a hole in that box, okay? And let's say that I'm standing right here. Yeah, the quality of the engineering drawings just went right down the hill when I threw that stick figure. Okay, and let's say that I am looking at the box like this, okay? So what am I gonna see? I'm gonna largely see this face, right? So I'm gonna see this, okay? But I propose that's not what my engineering drawing is gonna look like. My engineering drawing is actually gonna look like that. Why did I draw this here?
There's a hole through it.
Because there's a hole through it, right? So I'm trying to represent that here's what the part looks like, right? But there's a hole here too. And so if I was looking at, let's say, the top view might look like this, right? And then the side view might look like that. And notice I'm using a very specific legend. Like notice how the line I drew through the center of the hole looked like that. I didn't choose that arbitrarily. That's typically what we do in engineering drawings. Notice how the hidden lines I drew like a dashed line. I didn't choose that arbitrarily. That's typically what we do. If you're having trouble conceptualizing what an object should look like according to its views, the analogy that we sometimes use is what's called a glass box. So the idea is, imagine wrapping a glass box around the object, looking at each side, and then if you were to unfold that glass box, that would be what the schematics look like. Does that make sense? In fact, it also helps you position where those schematics should go on the drawing. Okay. I'm going to stick on this slide a little bit because I kind of want to make a few points about this. Because this is going to seem a little counterintuitive, okay? But before we talk about like the content of this slide, I want to talk about like the information that you need to include on an engineering drawing. Okay, so let's use a really, really basic example. Okay, so I have, let's say, a metal plate, rectangular plate, what have you, and I have a hole in that plate. And notice how the hole is not in the center. Okay, it's not in the middle. Okay, and we'll say that this mark right here is where the center of the hole is. Okay, now I'm going to ask you a somewhat basic question. How many dimensions, how many data points do you need as a fabricator to be able to fabricate this as specified? Okay, now I propose all you need are 6 data points. All right, where are you coming up with 6? Okay, well, let me show you. So first off, I need this dimension. Here, let's make up a number. Let's call this 8 inches. And let's do a number here. Let's call this 10 inches. So we would obviously need the size of the plate, right? Okay. I propose we need 2 more data points, and that's where this hole is. Okay. Now, what I'm going to do, here's what I'm going to do. I'm going to say we need this dimension right here. Let's call it 3 inches. Do I need this dimension?
No.
Why?
You can 8 minus 3, 5.
It's not independent, right? So remember in math when you learned about independent variables versus dependent variables? Remember that? So that's sort of what's going on here with this 5 is that this is a dependent variable, okay? And I'm talking about a really, really simple part here, but what I'm saying is the more information that you put on an engineering drawing, A, the more stuff that you have to review and check, and B, the more potential for error, okay? So if you don't need it, don't put it down, okay? That's sort of my point, okay? Now let's go back to this. So we needed 3. We also need this dimension. Let's call this 6 inches. Okay? Now that's 4 data points right there, right? I propose that you need 2 more. Okay, so I'm curious. Can anybody tell me what those 2 are? Yes?
Depth of the sheet and the radius of the circle.
Okay. All right. So let's talk about that. Okay. First off, you're 100% right with one little correction. Okay. First off, okay, so let's talk about the thickness. Okay. So I propose all we need to do is put a note on the side. Actually, wait a minute. Hold on. All caps. Do I need a whole nother schematic to show that? I just say it, I don't need another drawing. Okay? Now, the other thing you said was what?
The radius was the diameter.
All right, let's talk about that. So, okay. I say it's the diameter. Okay? Now, for the diameter, what I will do is I will say, let's say 2 inches, and then the symbol we tend to use is something like that as a diameter. Now, let me ask you a question. I'm just curious. Why am I saying it's better to use a diameter instead of a radius? Now, I'm sure the math folks are like, well, it doesn't matter. It's all the same. Yeah, it's all the same, but why a diameter instead of a radius?
It's easier to measure in real life. Just holding up a ruler across the whole thing versus trying to find the midpoint.
You're really close. You're not wrong, but there's also, let me ask you this. Let's say this was a piece of wood. How are you going to fabricate this? So you're going to cut the board out, but then to cut this hole, what are you going to do?
2-inch hole. Yeah, 2-inch jigsaw.
You're going to drill, right? Or so like we tend to specify holes and diameters because that's how you spec out drill bits. Yeah, I mean that's pretty much it. Typically, I mean that's what I'm saying. Like usually, like a lot of the reasons for that just go back to real world. And I'm sure the math professors are like, well, it doesn't really matter. You're right, it doesn't matter, but we're building it. So what makes sense? I can go to Lowe's and buy a 1/2-inch drill bit. So that's what it's going to drill is a 1/2-inch diameter hole. We tend to spec out holes and diameters, but when it comes to arcs or fillets, we tend to spec those out in radii. Okay. All right. So now with all that said, let's go to this slide. So whenever you have an object, and again, you're the engineer, it's your job to tell the fabricator, to tell the contractor, to tell the manufacturer how to build this thing. How many views are enough? In general, you should try and use as few views as possible, not as many, okay? The more information that you include can lead to errors. It can lead to contradictory information. It means more stuff that you have to independently review. It reduces clutter on the drawing. It makes it easier to interpret. This is a brass shim. I only have one view. Is there any information missing to fully construct that part? I say no. It's all there. You don't need any else. If you need additional views, use them, okay? But don't make the drawings more complicated than they need to be, okay? It will cause problems down the road. Okay, so if we're talking about this part, so this is a good example of what I mean by eliminating unnecessary views. Let's take a look at this part, and what I really kind of want to focus on for this is the left view right here and the right view, the ones on either side of that center. Are they really giving you any independently unique information? It's just the same image, just mirrored, right? Why include it, you know? So don't do that, okay? Typical orthographic projection is a front, top, right projection. Just in terms of engineering practice, if you had to choose between the right and the left, if the right shows it equally well, you typically chose the right view. And if the top and bottom show things equally, you can see that as well, show the top view. Front, top, and right is sort of the standard for orthographic projection. Speaking of, this is a standard orthographic projection for a given part. Okay, the front view, so if you, let me go back to this slide here. So if we talk about orthographic projection, an orthographic projection typically contains the front, top, and right, and the front is the biggest. But again, you're the engineer, your job is to produce that drawing. How do you decide which is the front? Because if you have some object, like any side could be the front. It's like if I was looking at my iPhone, which side would be the front? I would say this is the front, right? This is the front, right? Okay, so here's the drawing. How would I draw my iPhone? Well, I would probably say this is the front, and I would probably orient it like this, because that's sort of like how I think of an iPhone. I might orient it like that, but I wouldn't orient it upside down. There's an argument to be made about whether a drawing of an iPhone should be like this or like this, but nobody would orient it like upside down, you know, because you don't hold an iPhone like that. We typically would choose the front view so that it has the highest number of normal surfaces, so normal to the page, and then we show that object in a usual, what we would call operating fashion. So like if I was drawing a car, I would probably choose the front view as like this. Like I think this is a really poor front view. I think this is a poor front view because it's sort of, it's not parallel, and I think this is a poor front view because the, I think that this is more clearly a vehicle than this. Just basic, you know, common sense and whatnot. Okay. Sound good? Okay. So one of the things that you will see in an engineering drawing is what's called a partial view or a break line. So let me sort of explain what I mean by that. And the easiest way to explain that, and my apologies for bringing up more civil engineering examples, but I think, actually, I don't know that this would really matter. I think this would apply to mechanical engineering as well. Let's say that you had a brace in a system, and let's say the brace is, I don't know, 20 feet long, and there's a connection here and a connection here, okay? So it's a pretty boring part, but the interesting stuff happens right here. Does that make sense? So what I might do is I might say, okay, let's sort of focus on what's going on right here. So let's, you know, we got this bolt, this bolt, this bolt. Then after a while, like nothing really matters, so we'll draw what's called a break line. And basically all this break line means is that the part just goes on this way, okay? So a break line could look like this, or, you know, it could just, you know, look something like that. Either one is considered fine. So if you ever see that, that's what this means. So in the case of, for example, this part right here, you can see we're looking at this hole, and then the part like just goes on, and all we really care about is what's going on right here. Does that make sense? That's what a break line is. All right, cutting a section. Again, secret weapon of structural engineering is a samurai sword or a lightsaber if you're a sci-fi fan. Section views are intended to represent the internal features of an object. So like the classic example is like, if I have a melon and I cut a section, there's a good reason for doing that from an engineering perspective because we can see the internal structure of the melon. We can see the seeds. We can see what's going on inside. A common example of where you might see that is, for example, in axis symmetric parts like wheels and bearings and things like that. If we cut a section, we can see what's going on the inside. Okay, so just so everybody is aware of the nomenclature, the terminology of this line. So if I have a let's see, how do I want to do this? Let's say I have a plate and I have a hole in it, right? And I want to cut a section and I want to look to the left, right? So the idea is that I would cut a section and look this way. And so the idea behind that would be taking the samurai sword or lightsaber, cutting through, and what I'm doing is I'm looking at this side. So the idea is I'm looking here, and I'm looking at this. And so what do I see? I see that. Maybe I see that. So like that's where, the hole is and whatnot. Does that make sense? So the arrows of direction where it's sort of like you can sort of see it like right here, where the line sort of like does this sort of thing like that and the arrows point that way, that indicates which direction that you're looking. Does that make sense? You okay with that? Okay. How are we doing on time? Oh, we're doing good on time. Okay. Pictorials. Okay. So a pictorial is when so actually let me go back to the very beginning to sort of explain the pictorials. If you remember this drawing right here. So if you remember, this drawing was this is the first drawing I showed you, and there were a series of two-dimensional representations, but notice how that image in the top right really helped clarify what we were looking at. It's like this 3D rendering. That's a pictorial, okay? So whenever you have like a 3D rendering of a part sort of included in the drawing to help the engineer or the fabricator understand what you're looking at, that's a pictorial, okay? There are a couple of ways that you could generate a pictorial, and this goes back to that whole high school exercise where, I've got here a stapler, and the artistic way of doing it might be drawing it in perspective. There's a couple of different ways of doing it. I will tell you in engineering schematics, we don't use perspective very often, okay? And I'll show you why, but let's go through the two that are most common. The most common is an isometric pictorial. So the way an isometric pictorial works is we have X, Y, and Z axes. What we do is we split those at 120 degrees and we draw the object that way. The reason why an isometric pictorial is so popular on an engineering drawing is that if you maintain your X, Y, and Z axis that way, then that means that you maintain equal scale among all three directions. That you can actually use an engineering scale and measure an object either along the X, Y, or Z axis, and the scales will be maintained. Conversely, that's why we don't like to use perspective images. Do they look better? Yeah, they look better, but they don't maintain mathematical scale like an isometric view does. Either an isometric pictorial or an oblique pictorial works where scale is maintained. And that's really where a perspective pictorial fails. It looks good, yeah, it looks great, but it doesn't maintain scale, okay? So that's why we don't use them very much in engineering drawings. Does that make sense? Okay. All right. I'm going to close this off with some discussion of construction drawings. So this is mainly for you civil engineers in the room. So when we're doing construction plans, the idea is to sort of convey the means of turning the field site from a field site to an as-built final project. And so it does need to convey materials and quantities, dimensions and locations, notes and obviously views of the finished product. But a couple things that are worth mentioning on civil engineering drawings: pictorial views are not as common. And the other thing is that the views have very standard conventions. Okay, so this again, I'm sorry, like bridges actually serve as a very nice way of explaining the views for civil engineers. So if we're looking at a bridge, okay, the terms that we use are a plan view, a profile view, and a cross-section view. A plan view is, so the idea behind a plan view is, imagine being in the helicopter looking down, okay? So what are you going to see? You're going to see the road. And so the idea is that a plan view will contain the length of the project, the width of the project, but a plan view does not contain elevation. It does not contain information, up and down with the direction of the earth, okay? This is an example of a plan view drawing. Notice how a north arrow would need to be included in plan view. Okay, what about profile view? And sometimes you'll hear profile view called an elevation view. They're both sort of mean the same thing. And a profile view or an elevation view would be like standing at the river looking at the bridge. Okay, so you can see the length of the bridge, you can see the elevation of the bridge, the height of the bridge, but it does not contain width, like in and out of the bridge, like across the lanes. Like you can't see that direction from like one lane to another. Okay. Whenever you look at an elevation view, you're not going to see a north arrow because it's not going to make sense. Okay. The other thing that you might see is different scales on different sides. So you might see a, this is a scale for the entire project. From here to here is like 600 feet along the length of the bridge, but from top to bottom, it's only about 30 feet. So we plot those at different scales so that you can really kind of see what's going on. And the idea is like the dashed lines on this profile view are the existing elevations. This is what the ground looks like now. And then the solid line is what it's supposed to look like when it's all said and done. And here you can see the bridge. So really rocky terrain to a smooth road. The cross-section view is samurai sorting or lightsabering through the bridge. So we can see the width of the bridge, we can see the elevation, we cannot see along the bridge, okay? And so these are some cross-section views. Again, no north arrow present on a cross-section view because that wouldn't make any sense. Okay, let me take a step back. I got some housekeeping items before you leave. Anybody have any questions? So again, the quiz is going to open at 1 p.m. today. It will close 10 a.m. on Wednesday, okay? Unlimited attempts. Just make sure you have it done. I don't think you'll find it's very challenging, okay? I'm going to pull up the QR code one more time. That's all I got, everybody. I will see you all maybe on Friday, but definitely next Wednesday. Have a wonderful break. You have a holiday on Monday.